So today we are talking about binary tree. So first of all, binary tree is basic binary tree. I'll tell you what is in the binary tree first of all. So binary tree is like a basic tree. So this is the root node. Now the tree can have like multiple childs, like one, two, three, any childs. So this is the basic tree, but the most important topic in the tree is a binary tree. So today's our topic is binary tree. Now binary tree, each node have at most two children. Like this is the root node, so it should have like left child and a right child. Like only two childs are possible. Then there is a strict or proper binary tree. Each node can have either 2 or 0 children. As you can see, this is the root node, two children. Now it has one children, but this has two children. So like either 2 or 0 children. Like it should go from 0, 1, 2. They cannot have more than two children. Now here I have shown you the level of levels. So it goes in the power of 2 to the power k. So like level 0 to the power these are the levels: level 0, level 1, level 2, level 3. So if you want to find the maximum number of nodes, it goes as max 2 to the power k or I. You can take whatever you want. So according to this is I is the level. So to the power 0, that means 1 level. To the power 1, that is 2, 4, 8, and so on. Now there is a complete binary tree. All level except possibly the last are completely filled, and all nodes are as left as possible. So it is this is the same binary tree here. But the difference between this binary tree and this binary tree is it has been left side fill hona left side fill hona chahiye. Like most should be on the left side. The children should be directed towards left. So this is the binary tree. Now here, as you can see, this is the perfect binary tree. Perfect maximum number of nodes in a tree with height h. So this is the root. These are level specifies. This is for the perfect binary tree. The maximum number of nodes in a tree with height h. So before starting the concept, I will just show you this. So from root node to the node, you want to find the depth. So from root node to the x, the distance is called the depth, and from that from that node which you have specified, let's say x. So from x to the leaf node, that is the height of the binary tree. Now for perfect binary tree, height of the perfect binary tree with n nodes is log base to n plus 1 minus 1. This is a simple derivation of it. Low cost requires complete binary tree. This is the main thing you should know in a perfect binary tree. Now one more thing, that for perfect binary tree, maximum number of nodes are given by the formula 2 to the power number of levels minus 1. So height of the binary tree is given by log base to n plus 1 minus 1. Perfect binary tree is also a complete binary tree. Like perfect binary tree is also a perfect binary tree is also a complete binary tree, but all complete binary trees are not the perfect binary trees. Now balanced binary trees, this I'll show you further. Balanced binary tree. Binary tree is simply the height of the left subtree minus the height of the right subtree. So this is the root node. This is the left subtree. This whole is the left subtree, and this whole is the right subtree. So difference of left subtree and right subtree is given is the balanced binary tree. Height of the empty tree is minus 1. So like if you have learned the concept of stack, so if you want to point anything, so stack usually starts from the minus like a star. Here hash, star or hash, if you can it's your choice. But as you see, that is equal to minus 1. So like in the stack, in the implementation we have seen that top minus, so this is the minus 1. Now height of the empty tree is minus 1. Height of the tree with one node is 0. Maximum height is 1. More than 1 is not a balanced binary tree. Binary tree. Now we can implement binary tree using dynamically created nodes. Like as we have studied in linked list, this is the dynamically created tree. So this is the struct node into data, struct node star left, struct node star right. This is all we have covered in linked list. Now here we can see the arrays. So arrays, this binary tree can be also manipulated with using arrays. So here I have given the index number for the tree, 0, 1, 2, 3, 4, 5, 6. It goes in this pattern. So as we can see, array starts from index number 0. So whatever index number in the tree is given the index number of array. So now for getting the left child index and right child index, we use the formula 2 to the power I, no, 2i plus 1 and 2i plus 2. 2i plus 1 for the left child, 2i plus 2 for the right child. As you can see, for 0, so keeping the value 0 for 2i plus 1 we get 1, and keeping the right 2i plus 2 we get right subtree. And for tree, for first, as you can see, we have given this value. Arrays are used to implement heaps also. Now as here is the cost for arrays, linked list, and a sorted array and binary search tree. Now before introducing the concept of binary search tree, I would like to know that why we use binary search tree. As you can see, the searching for array is big O of n, and for linked list is same big O of n. As you can see, insertion and removal both are same. But when we talk, this is for the unsorted array. When you talk for this sorted array, the search time is big O log n. Here the drawbacks of unsorted array are used by sorted array. Now for binary search tree, the searching time is big O of n, and insertion is big O of log n, and here removal is also big O of log n. So all the drawbacks of arrays, linked list, sorted, unsorted arrays are covered by binary search tree. So let's go to binary search tree. Binary search tree, value of all nodes in left subtree is less, right subtree is greater. So root and left subtree or like lesser or equal, and for binary search tree, right side is greater. As you can see here, 15, 10, 20. And again 8, 12, 20, 17, 25. This is a greater, this is a lesser. Now for root node, we have here, as you can see, 16. So this is not a binary search tree, as 16 is this. For this it is okay, for this it is okay. But if you see from the root node, 15 and 16, so this is a greater than root node, so this is not a binary search tree. Now binary search, as before going for the concept of binary search tree, I'll like to know, I'll just want to introduce the binary search. As we can see, we take the median of the search space and see whether the number is greater or smaller, and again then median see and till we get the number. So like search space is there, we get the median, and if you get the median between, then again we go for the median of this search space and find that we can find if we are able to find the data or not. This is the worst case of binary search tree, where big O of n is given. Insertion will also cost like search. So now I would like to go on the implementation of binary search tree. This is the base. This is the tree format, and this is the node format. As we can see, struct node into data, into struct node star left, struct node star right, and now let us go for the insertion. For insert, the basic thing is, for insertion or deletion, we first need to find the element. So like before. We need to find the element. So first for before insertion, I'll show you the search format. So struct node star search, this struct node star root into data. So root is the value, root is the thing which you want to search. So this is the recursive form. So if root is equal to null, and root so again if root equal to null and root's data equal to data, then we need to return root. Then again, if root data is less than data, then return search root right comma data. Root data is greater than data, then return search root left data. So this is basically for the searching. As you can see, it works like if you want to search 15, then here it will come, it will find that it is null or not, and if you get the root data, then you return the data. Like if you want to find the 10, then first it will come here, it will find if it is not, it will run this condition, then it will run this condition like 10, so it is lesser 15, so 10 it is lesser, so it will run the condition of left subtree, and it will search through here from this condition, and so on. Now this for making the new node as it is as you can, if you have learned in linked list. Now for insertion also you need to first for insertion you first need to search the element, and then you can insert. So struct node star insert struct node star node comma int data. If node equal to null, return new node. This is the new node function. I will call the new node function here. So just return the new node. If node, this is for if data if the node is empty or something. So if node data is greater than data, then node left is equal to insert node left comma data. So like new node node data is greater than data, then insert on the left side, and similarly this is for the right side. Now deletion, as we can there are three cases. Node to be deleted is leaf, node to be deleted has only one child, and node to be deleted has two children. So now here before introducing the concept, I will come to later. Now here also, as you can you have covered this part in linked list. Here struct node star delete. This is the delete function. The function should return pointer to root node, because root may change after deletion. Its address is changing, we need to return it back. So here the root, why we have used root, because we need to update the root repeatedly. Like after changing the value, after the updation of value, the root need to be changed. So that is why we have used root, and because of that we will get the updated value. If root equal to null, then return root. This is the basic. Else if root data is greater than data, then root left delete. This is the recursive function. Delete root left comma data. Delete function send address of the modified value to the root of the left subtree. Like deleted function, this delete function send address of the modified value, the value which is modified after deleting, it will send to the root of the left subtree. And again root data is less than data, then we delete the right thing. This is a basic thing which we have. Now we will see the case 1. No child. This is a leaf node. In the root, we have the address of the node to be deleted. The root, as I said before, root as the data which you need to be manipulated. Now delete. So here, case 1, no child. In root, we have the address of the node to be deleted. If root left equal to null and root right equal to null, then delete root. And root equal to null, return root. Root still has the address. After returning root, the link will be corrected. So like if we need to delete the root, so root value will have the null value, and it will return the value. Now the case 2 with one child. Else if root left equal to null, then we will save the root in the temporary variable, and in the root we will save the root right value, and delete temp and return root. As you can see here, null and 12. So 12 value will go in the temp, and then we'll delete the temp, and we will return to the root. And this is for the right thing in one child. Else if root right equal to null, the same thing, root left value will be going in this, and delete temp and root return temp. Case 3, 2 children. The one which we need to be deleted is the root, as you have seen. Else struct node star temp equal to find mean root right. So this was the concept I was talking here. So like if there are in 2 children, if you want to delete, then in the right subtree you find the minimum, and then make that manipulate it and make it as case 2 or case 1. And if you want to manipulate to the right subtree, then find the maximum in left subtree. then again manipulate it and do it to case 2 or case 1. So here struct node star temp equal to find mean. So this is the function which will call, like it will find the minimum in the right subtree. Then temp data will be going into root data, and root right equal to delete root right comma temp data return root. This is the function, recursive function for deletion. As you can see here, first step 1 is root right में से minimum value find करो. Like from root right you need to find the minimum value. Step 2, उसे स्टोर करो टेम्प वेरिएबल में. सो स्टेप 2 इज आफ्टर फाइंडिंग दैट वैल्यू विल स्टोर दैट इनटू टेम्प वेरिएबल. As you can see here, this is the root node, this is 10 left subtree and right subtree. Here the 13 is the minimum value, and we will store that in the temp variable. Step 3 is minimum value of temp में है, temp data की value root data में डालो. So temp's data value will go in the root data value. So we have two duplication here. So now to eliminate duplication here, we have seen that you can just cancel this link, and that this is a leaf node, so it was in case 1. So after deleting that we'll get this. So this is the final subtree after deletion. Thank you very much.